In the first decades of the 20th century, physics stood at a crossroads. Two revolutionary theories, each powerful in its own right, seemed fundamentally incompatible. On one hand, Einstein's theory of relativity painted a majestic picture of gravity as the curvature of space and time, governing the cosmos on the grandest scales. On the other hand, quantum mechanics emerged as the strange and counterintuitive framework for understanding the universe's smallest constituents, atoms, and the particles within them. The problem was stark. Einstein's elegant equations describing a smooth and continuous fabric of space-time clashed with the probabilistic and quantized nature of the quantum world. Nowhere was this conflict more apparent than in the realm of very high speeds and energies, where both relativity and quantum mechanics held sway. Enter Paul Dirac, a brilliant and enigmatic British physicist with an unwavering belief in the power of mathematical beauty. Dirac envisioned a single unifying theory, an elegant mathematical framework that could weave together the seemingly disparate threads of relativity and quantum mechanics. He believed that true elegance in a theory often pointed towards deeper truths about the universe. Dirac's quest was not driven by experimental anomalies or inconsistencies in existing theories. Instead, he was guided by a deep-seated conviction that the laws of nature, at their core, must be both beautiful and consistent. This unwavering faith in the power of mathematical elegance would lead him to one of the most profound and unexpected discoveries in the history of physics. In 1928, Dirac achieved what many thought impossible. He formulated an equation that seamlessly merged Einstein's special relativity with the quantum mechanical description of the electron, a tiny particle carrying electric charge and orbiting the atom's nucleus. This equation, known ever after as the Dirac equation, was a triumph of mathematical elegance, capturing the essence of both relativity and quantum mechanics in a compact and powerful form. Imagine the equation like this. It's describing a wave, but this wave isn't like the ones we see in the ocean. This wave carries information about the electron, its spin, its movement, and how it exists within the fabric of space-time. The brilliance of Dirac's equation lies in its simplicity and its ability to predict the electron's behavior with incredible accuracy. But the equation held a profound surprise. While seeking solutions, Dirac encountered a mathematical oddity. Alongside the expected positive energy values, which described the familiar electron, the equation also yielded solutions with negative energy. This was deeply puzzling. In the everyday world, energy is always positive. It's what makes things move, change, and exist. The notion of negative energy seemed nonsensical. Dirac, however, was not one to dismiss mathematical results simply because they seemed strange. He understood that mathematics often reveals aspects of reality hidden from our immediate perception. The negative energy solutions hinted at a hidden realm, a mirror world existing alongside our own. Faced with the perplexing negative energy solutions, Dirac, ever the imaginative thinker, proposed a bold and unorthodox interpretation. He envisioned what he called the Dirac sea, a vast, unseen background filled with an infinite sea of negative energy states. These states, he argued, were usually occupied by electrons, effectively rendering them invisible to us. However, if an electron in the negative energy sea were to be excited and jump to a positive energy state, it would leave behind a hole. This hole, Dirac theorized, would behave like a particle with the same mass as an electron but carrying a positive charge. At the time, no such particle was known to exist. This was a truly revolutionary concept. Dirac's equation, born from the pursuit of mathematical elegance, had unexpectedly predicted the existence of antimatter, a mirror image of ordinary matter where particles have the opposite charge. It was a prediction so bold, so seemingly outlandish, that even Dirac himself initially hesitated to fully embrace its implications.